Okay, and this is an important note from a history of the theory of probability. One of the important names in the start of this whole theory is Antoine Gombaud, or however heck anyone who speaks French can tell me how to pronounce this. He was also known as the Chevalier de Mere. This is a Chevalier is a title of nobility, like Duke or another. It's a lower one. He actually did not have any title. He had studied at Mere, or Mere, however you pronounce this, and he adopted this as a nom de plume, or he was a kind of a writer and a self-styled philosopher, and he developed this name as a name he wrote under, but it actually was not his name. This is the man's name, and he was also a kind of serious gambler. So he had this game he'd play, and I don't know if he invented it or not. The stories are different depending on where I read it. But rolling 4 dice, the bet was, I bet I get at least 1 6. Now this was his thinking. Getting a 6, of course, we look at a dice, there's 1 6 out of 6 sides. So the probability by the basic law, which he had correct, was 1 out of 6. But here's where he was actually way off base. He thought, well, if I add up 4 of these, 1 6, I get 4 out of 6, so I should win 2/3 of the time. So he was very excited about this bet because he thinks, oh, I'm going to win money 2/3 of the time, I'll only lose 1/3, make a lot of money. Now we can already see that this thinking process is not sound. It's just not good. Because what if you threw 7 dice this way? You would end up adding 1 6 7 times and getting 7 out of 6, or a number larger than 1. And yet we know it is possible to throw 7 dice and not get any 6s. Okay, I just threw 3 and didn't get any 6s. If I do it again, according to his method, this what you just saw was impossible. If I add 6 6s together, if I had 2 more 6s to that, so if I add these together 6 times, I would have 1. You just watched me roll 6 dice and not get it. This is telling me it's certain. I have to get a 6 and 6 dice. And of course you know that. If you've ever played Yahtzee, you can throw dice after dice trying to get some certain number and you just don't get it. Okay, so his logic wasn't good. So we know his thinking was bad. So how would we actually calculate his probability of winning? I'm going to let A be the event. I get at least 1 6. And then I'm going to let not A, or I don't have to let not A be anything. It is actually going to be the event you get no 6s at all. Because you either get none at all or you get at least 1. There's no other thing that can happen. You either get 0 or more than 1 or more. Now the reason I'm doing that is not A is actually going to be easier to calculate. And from the first lecture on probability, the first video, we saw that the probability of A and not A adds to 1. So I can solve for the probability of A. I can take 1 or 100% minus the probability I don't get what I want, and that'll also give me the probability I want. And this will be a little bit easier to calculate. Now on each dice, and this is quite easy to see, there's 1 6, so obviously there are 5 other numbers. So the probability that die doesn't give me a 6 is 5 out of 6. Likewise, so is the next one. And so is the next one, until I throw 4 of them. Well, I actually have 4. Look in my bag of dice here. And as you can see, I just threw 4 and I didn't get any 6s. And they are independent. Those rolls don't affect each other one little way at all. So we can multiply each of those probabilities of not getting a 6. 5 6 times 5 6 4 times, which is the same thing as 5 6 to the 4th power, and I get 0.482. Now we remember, this is the probability of losing. It's probability of not winning, 0.482. So if we lose 0.482, 1 minus that, or 0.518, gives us a probability of winning. So we should put a smiley face here. We're going to win more than half the time. Notice this is not near as good as he thought. He was thinking he was going to get 0.66 forever, or 0.67. It's a long ways down from that, but it is still a good bet. So wrong math, but it was a good bet. So on this game, our friend was making some money. However, nobody wanted to play this game for very long. So he invented a new game. A new game was the following. Rolling a pair of dice, so rolling 2 dice, probably get at least a pair of 6s. Now you know this is not likely. I can throw these for a long time. There's 1, but I'm not going to get a pair so easily. In fact, from our previous chart, we've already seen the only way you could get a pair of 6s, there's one way, and there are 36 things that can happen. So 1 out of 36 times are we going to get a pair of 6s. But we've got 24 chances. His thinking, the same as it was incorrect on the first problem, was he could add these up. 1 over 36 plus 1 over 36, 24 total of those would give him 24 to 36, or 2/3. This would be the same odds he thought he had in the first game. Of course, he was wrong in the first game, and we'll see what happens in reality in this game. Actually, and we're going to do the A and not A. So A is the probability to get at least a pair of 6, at least one pair of 6s in 24 rolls. Not A is that you get no pair of sixes in all 24 of your rolls. So we're going to calculate this one because it's easier, and instead of having to concern ourselves with getting one pair or two or three or any other number that could possibly happen, we can just handle no pairs of sixes. That's easy for us. And then we'll subtract that number from 1 because you have to either win or lose this bet. There's nothing in the middle. So not A. On an individual pair of dice, there's one way of getting a pair of sixes, and there are 35 other things that can happen. 5 and 1, 1 and 5, combinations galore. 6 and 5 is a loss as well. So we have 35 over 36 ways that this dice can come up wrong for us, not give us a pair of sixes. And we're going to do this 24 times. So we multiply them 24 times. Of course, that's boring to type on the calculator, so we use a power, and we get 0.509. This is our losing percent probability, so 0.509, or almost 51% of the time we're going to lose. 1 minus that 491, 0.491 is the probability we're going to win. So we're going to win less than we're going to lose. So this time, with his wrong thinking, he thought he had a good bet, but it was actually a bad bet, and he lost. The legend is he lost substantial money making this bet. Now, we keep talking about gambling, and I want to throw something out there for anyone who's, and I'm actually going to Vegas for a math conference next week, but I'm not a gambler. I view gambling my money as foolish, and I make bets where I think the probability is in my favor, such as buying underpriced homes and buying stocks that have good, what for my research seem to be good prospects for the future. I want to play games where the odds are in my favor. But a lot of people have some severe problems with gambling. It stimulates parts of their brain and, in ways that psychologists are still studying. So the point of this list here is most people with a serious gambling addiction won't get help until they've lost 2 of these: spouse, house, or job. Pretty serious things. You'd think if you lost your house, you'd be ready to get some help. So some research I've read shows that gambling addiction is actually harder to cure than heroin. So I just want to say this at this point. We keep talking about betting games. The theory of probability started, after all, with this gambler who we've just discussed. But if you have some kind of gambling issue, you really want to face that. It's in your benefit to recognize the problem and get help immediately, rather than waste away your job, your house, your spouse, some combination of those items.